So far in this course, we've looked at different ways to vectorize documents, and with each new technique we looked at, we managed to encode more information into the vector. Now, all the approaches so far have ignored word order, but we know that's not how language works. After all, what makes speech and writing coherent is ordering words effectively to express an idea. So in this module, we're going to look at how to capture the sequential nature of language through a concept called recurrence. To recap what we've learned so far, we started by looking at a few simple bag of words techniques including binary, frequency, and TF-IDF. Each document vector was as long as the vocabulary, mostly sparse, and didn't capture much else other than whether a particular word was present. We then looked at static word embeddings, which encoded some relative meaning of words. A document's vector then was the average of its word embeddings. This led to higher performing models, and it remains a common way to build a baseline model today, but still, it threw out word order. Assuming we're using a neural network, then in all cases we have to feed the network the entire text at once. What are we missing by doing that? Text is a type of sequence, much like speech, music, daily stock prices, and sensor readings. It can vary in length, and with increasing length, offer more context and signal. But a standard feed-forward neural network doesn't process a single example as a sequence, so the variable length of text is something we need to deal with. As we saw in a previous demo, two sentences which mean different things but use the same set of words have the same bag of words, and so these two sentences, dog bites man and man bites dog, need to be differentiated. The word order of a sentence gives rise to certain themes and emotions. When I see a sentence like, "the dog looked guilty," it's amusing to me and paints a certain picture. In contrast, a sentence like, "the defendant looked guilty," is less amusing, unless of course the defendant is a hater or an enemy. The impact of the phrase "looked guilty" is dependent on an earlier word. Just a single change in noun completely changes the sentence and context because reading is a stateful process. Our interpretation of writing changes as we take in more input. Word order also controls the level of influence a word has in a sentence and other factors such as negation. When there's negation in writing such as the phrase "not good," the influence should be more localized to that area rather than spread across the entire passage. To better capture these qualities along with context, we can process sentences as sequences rather than bags. One approach is to do that through recurrence. Consider the standard neural network. We have an input X going into some hidden layer H. The output of the hidden layer is passed to an output layer, which has some activation function to produce an output Y hat. We'd like to process the sentence, "the dog looked guilty," as a sequence where each word is represented by a word embedding. So to start, we pass the encoding for the word "the" into the neural network. Now what? If we just pass in the encoding for the word "dog," it'll be as if the neural network is looking at a new, independent input, and there will be no connection to the previous word. There is no memory, so to speak. We need a way to link the word "dog" as part of the same input. The approach here is to add a recurrent connection where we feed the output of the hidden layer back into the hidden layer itself for the next word in the sequence. The hidden layer then receives two inputs, the current input X, so the embedding for the word "dog," and the output of the hidden layer for the previous word, "the." More formally, we say it receives the hidden layer output from the previous time step. To clarify this, we can add subscripts, so X sub t, H sub t, and Y hat sub t are part of the current time step, and the recurrent connection feeds H sub t minus 1, the hidden layer output from the previous time step, into the current time step. This forms a simple recurrent neural network, or RNN. An RNN is less an architecture and more of a concept. As we'll see, there are different architectures which use recurrence. This is a view of an RNN unrolled over time, so it's the same RNN at different time steps, so we can more easily visualize what's happening. So to process the sentence, the encoding for the word "the" goes into the network at T1, and the corresponding Y hat is generated. At T2, the network takes the encoding for the word "dog" and the hidden layer output from the previous time step, carrying information about the word "the." These are combined to produce an output for the second time step. The critical thing here is that Y hat at T2 is based on the sequence "the dog," and in this way, information about the sentence is carried forward through the network over time. At T3, same thing. Y hat at T3 is based on the entire sequence up to that point, which is "the dog looked," and finally at T4, the last Y hat output, it takes the entire sequence into account. So at each time step, the network creates a representation of the sequence up to that point, and through this recurrent mechanism, the network has some sense of memory. Let's clarify this further with a bit of math. RNNs typically use one hidden layer, though there's nothing stopping us from having multiple layers, but for our purposes, we'll stick with one. The input x is multiplied by a set of weights u. These are the weights going from the input layer to the hidden layer. The hidden layer output is multiplied by a set of weights v, the output layer weights, before going through some activation function to create y hat. So y hat is v times h sub t, run through some activation function g, such as a sigmoid or softmax. So far, this is the same thing as a regular feed-forward network. The big difference is in the recurrence. The hidden layer output is multiplied by another set of weights w before being fed back into the network at the next time step. The hidden layer output, h sub t, then is calculated by u times the input x plus w times the previous hidden output. And that summation is run through some activation function f, which can be relu or tanh. These weights, u, v, and w, are trained via backpropagation. And that's how the network learns how to best model a sequence over time steps. I'm not explicitly showing the biases here, but of course, we need to include those as well. So going back to our unrolled network to finish up with a few details, first, the same set of weights is used at each time step, and it's 3 sets of weights which are being trained. There's often confusion about RNN terminology. For our purposes, we'll call the hidden portion of an RNN a cell, and inside the cell can be whatever architecture as long as there's some recurrence happening. You might have wondered what h is at t0. Often it's just a zero vector, but as we'll see, we can also have a particular value for h at t0 which can inject some initial context into the network. With regards to the outputs, whether we use all of them or only the output at the end of the sequence depends on the goal. With an RNN, we can start doing additional tasks such as sequence labeling, where each y hat is a label for its corresponding input. In this example, the RNN outputs a part of speech tag for each input, and because we're doing a multi-class classification, the activation function used is the softmax. It would be the same idea if we were doing named entity recognition. On the other hand, if we were classifying a sequence, then one option is to ignore the intermediate outputs and use only the final hidden state, which can be thought of as an embedding for the whole sequence. This can be multiplied by the output weights as usual and put through a sigmoid for binary classification, a softmax for multi-class classification, or even passed on to a downstream system for further processing. Another possible way to classify a sequence is to take the average or max of all the hidden states and feed that into a classifier. We'll cover how to train RNNs when we talk about language models, but for now, let's talk briefly about backpropagation with RNNs. We'll focus on the key mathematical details here, but if you want to dive deeper into things like derivations, I've included links in the notes. The important thing here is to have an idea of how this differs from regular backpropagation. Let's say we're training an RNN to do some sequence labeling. So at each time step, there'll be a y hat output which will compare against a training label. And using those, we can calculate a loss at each time step using some functions such as categorical cross-entropy. So here's the loss at t1, and it proceeds the same way through the rest of the sequence. The overall loss for a single sequence then is the sum of the individual losses at each time step divided by the number of time steps. This is for a sequence labeling example. If we were using only the final output from the RNN, then the overall loss would just be the loss value from the final output. So now we have our loss for a single sequence. In this simple RNN, we now need to update 3 sets of weights, v, w, and u. The principles we learned in the neural network modules remain the same. It still comes down to using the chain rule to calculate the gradient, multiplying the gradient by some learning rate, and subtracting that from the current weights. There's just a tricky bit involved in the derivatives. To update the matrix V, we need to find the partial derivative of the loss with respect to V. Now, multiple paths contributed to this loss, right? The overall loss is a sum of the losses from time steps 1, 2, 3, and 4. So what we need to do is calculate the partial derivative at each time step individually and sum them to arrive at the gradient. In this case, the calculation for a single time step is the same as a regular feed-forward neural network. Here, the loss depends on y hat, which depends on q, q being v times the hidden layer output, so the derivative there is the derivative of whatever activation function we're using, and q depends on v. So calculate that for each time step, add it up, and we have our gradient. Calculating the gradient for matrix W is a bit more complicated. As we saw with V, multiple time steps contributed to the loss, so we need to calculate the loss at each time step with respect to W and sum them up. Here's the partial derivative chain for the loss with respect to W for a single time step. The first two terms are the same from the calculation for V. The third term is how Q changes with respect to H, and that's simply V. The fourth term is the tricky bit. To make it clearer, we'll put that on its own line. We need to calculate how the value of the hidden layer at a given time step changes with respect to W. Let's say we're calculating this value for time step 4. So we have our first component describing how H sub t changes with respect to W. Now, there's a recurrence here. So the hidden value at the current time step is influenced by the hidden value at the previous time step, which in turn also depends on the same matrix W. So what we need to do is add that path. Here we have H sub t depending on H sub t minus 1, which in turn depends on W. Okay, but then H sub t minus 1 is influenced by the hidden value at t minus 2, which in turn also depends on W. So we need to add that path as well. Hopefully you see where this is going. Because W contributes to the recurrence, we need to sum the paths from the current time step going all the way back to the beginning, which is why this approach is called backpropagation through time, or BPTT. And the example we see here is for L at just one time step. We would then need to calculate the loss with respect to W at the other time steps and repeat this process. With the matrix U, it's the same story as W. The matrix U also contributes to the recurrence, and so the approach to calculating the gradient for U is the same as for W, except with different dependencies, of course. Okay, so that's backpropagation through time. As usual, the frameworks you use day to day all have efficient implementations for this, where values are cached during the forward pass, and the derivatives are far more granular than this, but the important thing is that you know the principles under the hood. So those are simple RNNs. They enable us to model contextual information over sequences, whether it's writing, speech, music, or sensor readings. RNNs aren't the only way to model these sequences. We can also use n-grams and Markov models. If you're not familiar with Markov models, I've included a link in the notes. Both RNNs and Markov models can process sequences which plain feed-forward neural networks can't. They can also handle variable length inputs from sentences to paragraphs. With an RNN, two sequences of different lengths can be mapped to the same sized output for comparison. But an advantage of RNNs over Markov models is that an RNN's final output can encode the entire sequence. So information all the way back to the first time step, which can be useful for situations where we need to capture earlier context. Whereas a Markov model typically looks back only a fixed number of time steps, which is akin to focusing only on the immediate surrounding context. That's in theory at least. In practice, as we'll see, simple RNNs fall short of this goal. So RNNs can help us label sequences and classify sequences. With this knowledge, we can now also learn about language models. Consider this sentence. She spent the day swimming in the blank. What's your guess? Lake? Reasonable. Ocean? Sure. Milkshake? Bleach? Probably not. We know that, given a sequence of words, the probability of certain words occurring next is higher than others. Language is predictable. A language is governed by rules and also our shared understanding of the world. And anything governed by rules is predictable. Put another way, some sequences are more probable than others. And that's what a language model quantifies. A language model determines the probability of a sequence of words. So from our previous example, the word lake following a particular sequence of words may be 0.6, I just made that up, whereas the word milkshake following the same sequence may be 0.02. More formally, the probability of a certain sequence is the product of the individual probabilities. So the probability of the first word occurring times the probability of the second word occurring given the first word occurred, and so on. Language models are foundational in NLP. They're used in speech recognition, translation, autocorrect and autocompletion, and text generation, which of course is required for everything from summarization to question answering to dialogue systems. You may have heard of or played with the famous GPT models. Those are language models. If you're watching this video, language models are part of your everyday life. And RNNs will provide our first foray into language models, as we'll see in the demo. Let's look at how we would train an RNN-based language model. Much like Word2Vec, training is self-supervised. We start with the corpus and segment it into pieces, whether it's fixed-size chunks, sentences, paragraphs, or documents. Each piece is now one training example. The longer each piece, the more expensive the training, because the RNN has to process and backpropagate across more time steps. For this module, assume we segment our corpus into sentences. Let's say this is a fragment of one of the training examples. We have a word embedding for each word. Training begins by feeding the first word embedding into the RNN. This is the first time step, so the previous hidden state at this point is a 0 vector. The embedding goes through the hidden layer, and a softmax in the output layer creates a probability distribution over the entire vocabulary. Y hat then is each word's probability of being next in the sequence given what the network has seen so far. In this case, the word she. Now, we want to train the RNN to assign a higher probability to the next word based on the training data. In this case, the expected next word is swam. So what we can do is use the next word in the training example as a target for the current time step. So now we have a target y, which, as we've seen, can be a one-hot encoded vector or an index for the correct word, and a y hat, which is a probability distribution. If you recall from Neural Network Foundations 1, when we have a situation like that, the categorical cross-entropy loss is just the negative log probability of whichever y hat value corresponds to the target. In other words, the loss for the current time step is just the negative log probability of the word swam. And of course, the higher the y hat probability for swam, the lower this loss is going to be. And that concludes one time step. In the next time step, the next word in the training example, swam, is fed into the RNN along with the previous time step's hidden output, and a loss is calculated. In this case, the loss is the negative log probability of the word in from y hat. And this continues until we process the whole example, or more commonly, a batch of examples. At that point, we can calculate the overall loss and use backpropagation through time to adjust the weights to further minimize the loss. So at the beginning, the network will be guessing the next words in the sequence randomly, but over iterations should get closer and closer to mimicking the training examples. Note how at each time step, we're feeding the correct next word into the RNN. In this example at time step 3, the word in is fed to the RNN. By doing this, we're giving the RNN a more focused classification task. In this case, the inputs are the embedding for the word in and the hidden state vector representing she swam. The output is a probability distribution for each word in the vocabulary being next in the sequence. And once we have the output, we calculate a loss and ignore the output itself, and instead feed the network the next correct word in the sequence. This technique is called teacher forcing, and we'll see this in the demo. Once our RNN is trained, generating text is straightforward. It begins with feeding the RNN an initial token. This can be a special start token if you want the RNN to generate the entire sentence from scratch, or we can also feed a particular word token to prime the network. From there, the output layer has a softmax to generate y hat for this time step, which will be a probability distribution over the vocabulary. To determine the next word, this probability distribution is sampled. So the word that's picked doesn't have to be the one with the highest probability, but a word that's likely. And that's a simple way to inject some variety into the generated text. In this case, let's say it's the word the which ends up getting picked, which is reasonable to expect as the beginning of a sentence. From there, the RNN cell at the next time step takes the value of the hidden output from the previous time step, and it also needs to take in a new X input. The X input in this case will be the sampled word from the previous time step, the word the. And once again, the output layer softmax creates another probability distribution over the vocabulary which gets sampled, and let's say the word cat gets sampled during this time step. And it goes on like this from there. Each new word is generated by sampling from a probability distribution that's based on the sequence up to that point. And it continues like this until a certain limit is reached or a special n token is outputted. Generating text in this manner is an example of autoregressive generation. Keep in mind that whatever your RNN generates is entirely conditioned on the corpus it was trained on. So if you train an RNN on Shakespearean text, the output will look vaguely Shakespearean in its wording and cadence. You can even train an RNN to spit out cooking recipes or driving directions. There's no promise any of the output will make sense, and if you're training this at home, it probably won't. But the output will look and sound like the training input, at which point one could use other techniques to refine it. Even with the state-of-the-art models, which take millions of dollars to train and where the output starts looking impressive, there's the problem of biases in the corpora, which is a whole other topic on its own. But let's continue. Once the RNN is trained, how do we evaluate it? A language model determines the probability of a sequence. So if a language model is good, then it should give high probabilities to sequences in some test set because it has learnt which sequences are probable and which are not. The popular metric to measure this in a language model is perplexity, but rather than raw probability, perplexity measures the inverse probability of the test set. So it's 1 over the probability of the entire test set. And that's also normalized by the number of words to control for different train versus test lengths. By taking the inverse probability, we get a score to minimize. Conventionally, the lower the perplexity score, the better. And I've included a link to perplexity scores of various models in the notes. Just keep in mind that as perplexity lowers, there should be fewer grammar errors, and the text should get more natural sounding. But human writing and speech itself has a particular perplexity score. So getting a lower perplexity score than that may produce text sounding somewhat artificial. Just something to keep in mind. Okay, so that's an introduction to language models, and we'll revisit them throughout the rest of the course. Back to the topic of RNNs in general. One of the benefits we stressed was an RNN's ability to model an entire sequence going all the way back to the beginning. And this is useful because often in language, there are long-range dependencies. Consider the sentence. He was supposed to meet his friends at the show, but something came up at work, so he called blank to say he would be late. A reasonable guess for the missing word is them because he was supposed to meet his friends, a group of people. There's nothing special about this example. We see these kinds of dependencies every day. But for an RNN to guess the word them as opposed to he, she, they, or something else, it needs to somehow model the relationship between them and friends, and this relationship spans across over a dozen time steps. This is where simple RNNs begin struggling. One issue is that, as the sequence gets longer, information from the earlier part of the sequence gets diluted, because there's no way to control what to emphasize over time. In that sense, simple RNNs have a stronger local context at any given time step, despite technically being able to encode the entire sequence. But the more serious problem is that of vanishing and exploding gradients. As we've seen, backpropagation involves repeated multiplication, and in an RNN that happens across time steps. If there are a lot of time steps and the weights are small enough, the resulting gradient eventually shrinks to 0 and the network stops learning. Conversely, if the weights are large, the gradients eventually explode, which leads to instability or overflow errors. So simple RNNs have a hard time learning long-range dependencies, and because of how frequent and important these dependencies are, simple RNNs are rarely used in practice. In the Neural Network Foundations videos, we talked about a few remedies for vanishing gradients, such as batch normalization, different activation functions such as ReLU, and other weight initialization techniques. There's also gradient clipping for exploding gradients. I've included a link about gradient clipping in the notes. But the more popular option is to use a different cell architecture altogether. One of these is the long short-term memory, or LSTM, a type of RNN cell architecture which addresses the shortcomings of simple RNNs and is more capable of learning long-range dependencies. In essence, each LSTM cell contains gates which control the flow of information. These gates are themselves neural network layers which can learn to amplify or dampen information as needed to model long-range dependencies. It'll become clearer once we step through how this cell works. First, the inputs. Like a simple RNN cell, an LSTM cell takes in the current input X and the hidden output from the previous time step. In addition to this, it takes an additional cell state, also from the previous time step. This cell state serves as an additional memory that stores long-term information, as we'll see. The previous hidden state and the current input are multiplied by weights and added together, the same as we would in a simple RNN. The result is then put through a sigmoid function, often referred to as the forget gate. Now, this is important to keep in mind because it's sometimes a source of confusion. This sigmoid is often thought of as taking in a scalar and squashing it to output another scalar between 0 and 1. But the input to the sigmoid function here is a vector. In this case, the sigmoid function gets applied to each element of this vector. So the output of this function is also a vector. This applies to the rest of the LSTM cell. What's being passed around and manipulated are vectors, not scalars. Because the forget gate is a sigmoid, the output will be a vector of numbers between 0 and 1, which we can call f sub t. The cell state from the previous time step is then multiplied element-wise by f sub t. Since f sub t is an array of numbers between 0 and 1, it acts as a mask to control which elements of cell state to pass through. So 0 means completely delete, 1 means completely keep, and any number in between means keep some proportion. And this is how a gate controls the flow of information through the LSTM cell, and we'll see two more of them. At this point, the cell has determined what information to remove or keep from the previous cell state. This mechanism allows the network to carry important information forward rather than having it dissipate. The next step is to decide what information to add to the previous cell state, and this is done through the input gate. The mechanism is the same as the forget gate. The previous hidden state and the current input are multiplied by a different set of weights and run through a sigmoid function to create another mask, which we'll call I sub t. The previous hidden state and input are also multiplied by another set of weights and run through a tanh function. This represents the new information available to be added. So now we have C tilde representing the new information available, and I sub t, which is a mask that controls which of the new information will be added to the previous cell state. C tilde and I sub t are then multiplied element-wise to gate the flow of new information. The cell has now determined what information to add to the previous cell state. The remaining step is to simply add this new information to create the new cell state. This new cell state, C sub t, can then be passed to the next time step. Okay, so the LSTM took the previous cell state, dropped some information, kept some information, then added some new information to it, and that led to a new cell state. The remaining item to be calculated is the new hidden state. For that, we have one more gate, which is the output gate. Once again, the previous hidden state and the current input are multiplied by a fourth set of weights to create a mask. The new hidden state will be drawn from the current cell state. To do that, the current cell state is run through a tanh function to create a vector of candidate values. These candidate values are multiplied element-wise by the output gate mask to determine which information to pick up. The result becomes the new hidden state. And so the hidden state is now carrying long-term information from the cell state. Note how this illustration shows the new hidden state exiting the cell at 2 points. The one at the top is intended for the current time step output, and the one at the bottom is intended for the next time step input. And that's the complete flow of an LSTM cell, and it has a much easier time learning long-range dependencies because through 4 neural network layers, it can learn what information to remove, what information to carry forward, and what information to add. LSTMs aren't the only alternative to simple RNN cells. There's also the gated recurrent unit, or GRU, which I've linked to in the notes. Let's finish before the demo by covering a few ways to combine recurrent cells. One popular way is to stack them. In Neural Network Foundations 2, we talked about how deep neural networks learn representations. That is, each subsequent layer learns how to combine inputs from previous layers into more useful representations given the goal. And we can apply the same principle using RNNs. An RNN processes a sequence and outputs another sequence. There's nothing stopping us from taking that output sequence and using that as an input to another RNN. From the RNN cell's perspective, it's just expecting an input from the previous time step and a current input. And we can repeatedly stack RNNs until at some point we produce the final outputs. By stacking these RNNs, we can build a network which can learn patterns which may be too complex for a single layer RNN. Stacked RNNs, for example, have seen great success in neural machine translation, and for a while Google relied heavily on multiple stacked RNNs to translate one language to another. How deep to stack RNNs depends on the application, and the training time increases quickly with each layer, so it's best to try a single layer RNN and see how that goes before adding more. Another common approach is bidirectional RNNs. For something like the English language, the standard RNN processes a sequence from left to right, accumulating context as it goes. Each y-hat that gets outputted is based on the sequence up to that point. But often we have access to the whole sequence ahead of time, and being able to incorporate future information can be useful, especially for labeling tasks. One example is part of speech tagging. Consider these 2 sentences: Brown refused to testify, brown sofas are on sale. If we had to give one part of speech tag to each word, brown in the first sentence would be a proper noun because it refers to a person, and brown in the second sentence would be an adjective because it refers to a color. But we know that only because we looked ahead. If we could see only the first word at the beginning of a sequence, like a standard RNN, then it wouldn't be so easy. To help RNNs be more accurate in these situations, we can add a second RNN that processes the same sequence in reverse order. So the RNN in blue here takes the last token in the sequence as its first input and makes its way to the beginning of the sequence. Y-hat is generated by concatenating the outputs of the 2 RNNs and multiplying it by a set of weights v to reduce it down to the expected dimension. In this way, the y-hat at the beginning of the sequence is informed by context from the rest of the sequence. So those are two popular ways to combine RNN cells, and you can even have bidirectional stacked RNNs if you think that's worth trying. Speaking of which, let's look at a demo. Alright, so here I've opened the NLP Demystified Recurrent Neural Networks Collab Notebook. As always, you can find a link to it on the module page or get to it through the NLP Demystified GitHub repo. And remember to enable GPU acceleration through the Runtime, Change Runtime Type menu option. Okay, so in this demo, we're going to accomplish two tasks we haven't before. The first thing we're going to build is a part-of-speech tagger using a bidirectional LSTM. So given a sequence of words, the model will output a part-of-speech tag for every word in that sequence. Part-of-speech tag datasets are difficult to come by because they're labor-intensive to create and many are behind paywalls, but fortunately, NLTK comes with enough corpora which are labeled with parts of speech. Here we'll use 3 of them, Treebank, Brown, and one from the Conference on Computational Language Learning. So these are sentences from newspapers and books which are labeled with their parts of speech. Each of the 3 corpora may use a different part-of-speech tagging scheme, so to make sure that all 3 we've downloaded use the same part-of-speech tags, we'll download the universal tag set. And you can learn more about these universal tag sets through this link here. Alright, so ADJ is adjective, ADV is adverb, and so on. Next, we'll retrieve the tagged sentences from each collection and combine them into one collection. Note how we're passing the universal parameter here to ensure all 3 collections use the same set of tags. And we'll also print the first sentence to get an idea of what the dataset looks like. Alright, so each example sentence is actually a sequence of tuples with the word at the 0 index and its corresponding part-of-speech tag at the 1 index. So the first 2 words here are tagged as nouns, the 4th token here is tagged as a number, and so on. And if you're wondering why this name is tagged as a noun rather than proper noun, it's because the universal tag set is simplified and doesn't have a proper noun tag. And we have just over 72,000 tagged sentences to work with. Since this is a sequence labeling task, the words are going to be the inputs to the LSTM, and their respective part-of-speech tags are going to be the targets. So the first thing we want to do is separate the words from their respective part-of-speech tags into 2 separate collections. And if we look at the first entry of the 2 collections, the sentences array now contains the input sentences, and the sentence tags array contains the corresponding part-of-speech tags. Before we move on, we'll do a quick sanity check here to make sure we have the same number of input sequences and target sequences. Okay, so that looks good. Next up, we need to create train, validation, and test splits. Since there isn't already a separate test set, we'll call split twice. We'll make it 75% train, 15% validation, 10% test. And this is the number of samples we have in each split. It's enough for our purposes. Alright, so we've pre-processed our data set a bit and split it into different sets. The next step is to vectorize. If you watched the demo from the last module on word vectors, this should look familiar. We'll start by initializing a Keras tokenizer using its default values, so it'll do some light filtering and lowercase, and include a token for out-of-vocabulary words in case we encounter words during testing or inference, which we don't during training. Next, we'll fit the tokenizer on the training set to create a vocabulary. As always, we're fitting on the training set only. The result is a vocabulary of about 52,000 words. Now, we need to create a second tokenizer because our targets are also sequences in this case. So we'll initialize a second tokenizer also with defaults and fit it on the target part-of-speech sequences. As we would expect, the vocabulary, so to speak, is far smaller here. We have only 12 part-of-speech tags. As mentioned earlier, keep in mind that since this is the universal tag set, it's simplified and doesn't have more granular tags such as proper noun. These are the possible tags in our data set. Okay, so we have tokenizers prepped for our input sentences and our output targets. We can now vectorize them. First, we'll vectorize the sentences by transforming them into sequences of integers, just like we did in the demo on word vectors. Okay, so that's what the first sentence looks like as an integer sequence. And just as a sanity check, we'll recreate the source sentence from the sequence to make sure everything is okay. And that looks good. Next, we'll do the same with the part-of-speech tag sequences using its corresponding tokenizer. So we're turning every sequence of target tags also into sequences of integers. And we'll do a sanity check on that as well. If we compare the part of speech tags with the source sentence, we see it makes sense. So heavy, interlobular, and connective all correspond to the adjective tags here. So far, so good. Next, we'll vectorize the validation sentences and tags as well. Now, as you know, one advantage of RNNs is they can handle variable length sequences. However, it can be beneficial to keep your sequences the same length. One reason is that your sequences may be very long, and the longer a sequence, the more time steps required, and the more expensive the resulting computations. So if you can still get good results with shorter sequences, then it can help to either truncate them or separate them into smaller sequences. Another reason is that sequences must often be the same length in a single batch. Not all batches, but within a single batch, the sequences within it often must be the same length. This means that if you want to process different length sequences, you can sort them by length, divide them into batches, and pad or truncate the sequences in each batch as needed. In our case, we're going to do the simplest thing and use padding to make each sequence as long as the longest sequence. In this case, that's 161. So we'll first pad all the input sequences to the same length. And if we look at the first input sequence, we see it's now padded. And we'll do the same with the target part of speech sequences. And finally, we'll also pad the validation dataset. Okay, so at this point, our train and validation input and target sequences are all the same length. All right, the last pre-processing step before we build our model concerns the targets. At each time step, sequence labeling is a multi-class classification task. And for this task, we'll use the categorical cross-entropy loss. And you may recall when that's the case, the labels need to be one-hot encoded. There's an alternative to that, which we'll get to later in this demo. But for now, as we have in previous demos, we'll one-hot encode all our targets. In this case, with Keris's two-categorical method. Now keep in mind that our targets are sequences of tags, right? Not just one target per example. So when we one-hot encode a sequence, what we get is a sequence of one-hot encodings, each representing a single tag. So if we look at the one-hot encoding of the first target sequence's first part of speech tag, it looks like that. We can convert a one-hot encoding back to its tag by determining which index is set to 1 using argmax, and then retrieving the tag corresponding to that index. In this case, the tag is a determiner. Next, we'll one-hot encode the validation target sequences as well. Okay, we're finally ready to build our model. We're going to use an embedding layer for the input tokens. So like before, we'll set the vocabulary size and embedding dimension. In this case, we'll use an embedding dimension of 128. And for the output softmax, we'll also set the number of classes for the output layer. Okay, so to create a part of speech tagger, we'll use a bidirectional LSTM, and composing this model introduces a bunch of new things. First, our sequences are padded. Almost all of these sequences contain zeros. We don't want our model to make predictions for padding because that's going to be easy and useless and lead to false training metrics where it thinks it's doing much better than it really is. So for the embedding layer, we're setting this mask 0 parameter to true. This causes the layers following the embedding layer to ignore padding. The second thing is the LSTM declaration itself. So here we're declaring an LSTM cell with 128 units for each of the internal gates. Since this is a sequence labeling task, we want our LSTM to generate an output at each time step. To do that, the return sequences parameter is set to true. The default value is false, and if that were the case, the LSTM would return an output at only the last time step. Finally, we're wrapping the LSTM in a bidirectional layer, so each output is influenced by the past and future since we have access to the whole sequence ahead of time. So essentially have two LSTMs, one processing the input left to right, another right to left. The output layer should look familiar by now. It's just a dense layer going to a softmax, and with return sequences set to true in the LSTM layer, the output layer will be applied at each time step. So those are the new things in this model. Other than that, the compile parameters are the usual things we've seen thus far. Keep in mind that I've set the random seed, and I'm using kernel initializers with fixed seeds so you and I get the same results. If you want different weight initializations, just remove these lines. Something to note here, we're using accuracy, but that doesn't mean the part of speech tags are evenly distributed. We're just using it here for convenience. If you want to use an alternative measure like precision recall, refer to the demo on naive Bayes. Alright, taking a look at the summary, the embedding layer is going to output a 3-dimensional vector of batch size, sequence length, and embedding dimension. Batch size is showing up as none because we haven't specified it yet. We will when we call model.fit. The sequence length is 161, and each element of that sequence is going to be a vector of 128, which is our embedding dimension. We declared an LSTM with 128 units, but because we're using a bidirectional LSTM, the output is twice the size, and that'll get multiplied by the output weights to reduce it down to 13 possibilities by the end. And now it's time to train. We're using early stopping here with the patience value of 3 because given the nature of the task, a little bit of overfitting is fine. I'll skip to the end. Okay, so the model stopped after epoch 8, and we can see the model got pretty accurate pretty fast. The validation loss is at its lowest at epoch 5, at which point it starts diverging from training loss, and then it goes on for 3 more epochs before stopping. Okay, so our model is trained. Let's try it on our testing data. We'll pre-process the test data the same way we did our training and validation data. And then evaluate our model on it. Okay, so the results are pretty good. We can now use our model to tag sample sentences. Here we're using 2 sentences from the slides when we talked about bidirectional RNNs. This function takes a list of sentences, vectorizes them and pads them, runs the model over them, and returns the sentences in tagged form. Keep in mind that we're tagging a sentence, so the prediction for a single sentence is going to be a list of probability distributions, 1 distribution per tag. So we need to convert each back to its original tag form. Okay, we'll give it a try. Taking a look at the tags for the first sentence, everything looks good. Brown here was tagged correctly as a noun. Again, keep in mind that the universal tag set doesn't have a proper noun tag, and everything else looks good. And taking a look at the second sentence, brown is correctly tagged as an adjective. So even though the word brown occurs at the beginning of each sentence, it still gets tagged correctly based on the later context because we're using a bidirectional LSTM. Alright, so that's one way to build a part of speech tagger using an LSTM. Industrial strength taggers will use more data, and nowadays more advanced models which create richer contextual embeddings. We'll learn about them soon. For now, on to our next model. Alright, the next thing we'll build is a language model by stacking LSTMs. For data, we'll use Sun Tzu's Art of War. The first step is to retrieve a lightly scrubbed copy from the NLP Demystified GitHub repo. Okay, so what we have here is the entire book as one long string. The next step is to start vectorizing. What we'll build here is a character-based language model. In a word-based language model, the model is given 1 or more words and asked to predict the next word in that sequence, just like we saw in the slides. In a character-based language model, the model is given 1 or more characters and asked to predict the next character in the sequence. The major advantage of character-based models is that the prediction space is much smaller. There are only so many characters in the English language compared to the number of words in a corpus, which can go from the tens of thousands to beyond. Character-level models can also pick up subtle aspects of how language works and better handle out-of-vocabulary situations. On the downside, character-level models need to learn longer sequences to make sense of a word versus a word-level model which already works at the word level. So to make sense of the word dog, it would need to learn the sequence pattern of DOG. We'll contrast word and character-based tokenization more and introduce a middle ground between the two when we talk about transformers. Keep in mind that RNNs process sequences, so what you learn here can be applied easily at the word level as well. So to that end, we'll initialize a Keras tokenizer and set the char level parameter to true, so that our corpus gets tokenized into individual characters. Everything else remains the same, so the tokenizer will still apply some default light filtering and lowercase. And as always, the first thing we'll do is generate a vocabulary based on the corpus. This time around, there's no separate training, validation, or test data, we're just training a model to generate language. If we look at the tokenizer's configuration now, we can see the tokenizer's vocabulary is actually a set of characters, and in addition to letters, that includes special Unicode characters for things like quotation marks. And in terms of vocabulary size, there are only 56 characters, as opposed to the tens of thousands of words that we're used to seeing by now, if you've been following the course. Next step is to do the actual vectorization. We'll vectorize the entire book into a sequence of integers where each integer maps to a particular character. So what we have now is a single array of integers representing the entire book, and there are just over 61,000 characters. And we'll do a quick recreation of the opening characters just as a check. Now, if you recall from the slides on language modeling, once we have a corpus, we need to segment it into pieces, and these pieces will be our training examples. For this, we'll use the TensorFlow Data API, which makes it convenient to build pre-processing pipelines. The first thing we'll do is turn the raw sequence into a TensorFlow dataset object. The dataset object is an abstraction over a sequence of elements, and we can apply transformations to these elements as needed. So what we're doing here is using the fromTensorSlices method to turn our raw list of integers into a dataset sequence of slices where each slice contains an integer. To make it clearer, here are the first 10 slices from the dataset object. Each slice is a tensor containing a single integer. We need to call take and convert it to a list because, like a Python generator, the dataset object is lazy. If we look at the first 10 elements of the raw integer list, we see they match. Okay, so what we've done is taken our list of integers and turned it into a sequence of tensors in a dataset object. We can now perform operations on it to further process our data. All right, next, we need to segment our corpus into fixed size pieces. For this demo, we'll make each piece 100 characters long. So in other words, each input to our language model during training will be 100 characters long, and so will be processed across 100 time steps. And we can create these pieces using the window method. A few important details here. The input time steps is set to 100, but the actual window size will be input time steps plus 1, so 101. And there's a reason for this that we'll get to further below. Here we're also setting shift to 1. This means that we'll create overlapping pieces shifted by 1. So imagine our input is 1, 2, 3, 4. The first piece will contain elements starting from 1. The second piece will then contain elements starting from 2. So each window is created by shifting the input by 1. And this will become clearer once we look at it. The reason why we're doing this is simply to have more training data. Lastly, this drop remainder parameter is set to true. This means processing will stop when there are fewer than 101 elements remaining. The remaining elements will be dropped. This way, all our pieces will be a uniform size of 101. Okay, let's take a look at the first 3 windows. All right, so each window is of length 101, and you can see the first window starts at 27, then goes 21, 1, and 8, and so on. The second window starts at the next integer, 21, and goes from there. You get the idea. The window size itself can be treated as a hyperparameter, but this will work fine here. One small snag here is that the window method returns dataset objects. So each piece is no longer a tensor, but is itself a dataset object. So right now, we have a dataset of dataset objects. But our model will be expecting tensor inputs, so we need to convert those window objects back into tensors. And we can do that using the flatmap method, which takes a nested list of elements and returns a single list of them. Now, at the same time, we do want to retain the pieces we just created. We don't want to go back to having only one long sequence. So we're also calling this batch method with flatmap to retain our pieces. Okay, so now we're back to having a single dataset object, and if we look at the first 2 elements, we see they're regular tensors, each 101 elements long. We're going to use batch gradient descent to train our model, so the next step is to divide our dataset into batches. Here we're using batches of 32. Before creating these batches, we'll first shuffle the data to improve our chances of finding a good minimum, and then we'll create the batches. This 10,000 parameter here is a buffer size, which you can learn more about through this link. And if we look at the first 2 entries of our dataset now, we can see each element is now a batch of 32, with each sequence in that batch being 101 elements long. All right, so we have our batches. Now we need to create our separate X input sequences and Y target sequences. In the slides, we talked about teacher forcing, where at each time step during training, we feed the model an input from the sequence, then compare the model's output to a target for that time step. And the target is the next character from the input sequence. From that, a loss is calculated. Then at the next time step, we feed the model the next element from our input sequence, not the model's previous output. and that's why our window size is 101 elements long. Each input sequence is going to be the first 100 characters, and its corresponding target sequence will be created by shifting over by 1, so the last 100 characters. And this will become clearer once we look at the results. So here, we're mapping over the batches and splitting each batch into 2 collections. The first collection will contain sequences excluding the last character, so the first 100 characters, and the second collection will contain sequences excluding the first character. Taking a look at the first batch, we see it's now split into 2, an input sequence and a corresponding target sequence. For greater clarity, let's look at only the first input and target sequences from the first batch. Okay, so here's the input sequence. It's now 100 elements long, and its corresponding target sequence was generated by shifting over by 1. So when this first input element is fed to the model, this will be the target. When the second element is fed to the model, this will be the target. The last step is to one-hot encode our inputs, not our outputs, but our inputs. In contrast to the last few models we've built, we won't be using any embeddings here. We could, but with just a few dozen possible characters, we don't need to. And besides, there's no reason why a particular letter should be closer to another in vector space, in this case. So, since we're not using embeddings and our input is categorical, we need to one-hot encode them. And we do that by mapping over our batches and applying the one-hot method to our input sequences. Note that we're leaving the label or target sequences alone despite them also being categorical. This is because we'll be using a loss function which can handle integer labels. More on that soon. And if we look at the first batch again, by the way, the batch will look different each time now because taking is a lazy process and we're pulling from a shuffling pool. We see the input is now a sequence of one-hot encodings, and the target sequence remains unchanged. As a finishing touch, we'll also call prefetch on our dataset, which is an optimization step. This instructs TensorFlow to read data for the next time step as the model trains on the current time step. We're using AutoTune here to ask the model to adjust the prefetching dynamically. Okay, after all that, we're ready to build our model. A few new things here. First, there is no embedding layer as mentioned. Second, we're stacking 2 LSTMs, so the sequence outputs of the first LSTM will be the sequence input into the second LSTM. We're using recurrent dropout here, which randomly drops the connections between recurrent hidden units. So dropout is applied horizontally across time steps. Check out this paper here for a more detailed explanation. And you can still use regular dropout here, which will randomly drop connections between input or output, but we're not doing that here. We're specifying the input shape in the LSTM because normally we'd specify the initial shape in the embedding layer, but since we don't have one, we're specifying it here. Lastly, rather than categorical cross-entropy, we're using sparse categorical cross-entropy. The idea is the same, but sparse categorical cross-entropy allows us to provide labels as integer encodings and skip the need to one-hot encode. So this is the loss function I was talking about, and it's why we don't need to one-hot encode our labels for this model. We could have used this loss function in our earlier models, but it was good to ground ourselves in why and when one-hot encoding is needed. Looking at the model summary, because we're not using embeddings, we have relatively few parameters in this model, and of course you can experiment afterwards with adding more hidden units and adjusting dropout and so on. Before we train, we'll set up model checkpoints, which we haven't done so far in this course. This model took a few hours for me to train, so as insurance we're using model checkpoints here. This callback saves the model to disk after every epoch. This way, if something goes wrong with our system during training, we can reload the weights from the last checkpoint and resume training from there. And saving these checkpoints is just a matter of supplying the callback to the fit method. Now, I've commented out the fit method here. Since this model takes a few hours to train on Colab, I trained it prior to this recording and saved it. Note how in the fit method, we're just passing in the batches as is. There's no need to supply separate input and target sequences because Keras can work with TensorFlow dataset objects. Feel free to uncomment this and train your own model if you like. And unless you're paying for Colab, I suggest training it on your local machine. And once a model is trained, saving it to disk is easy. Alright, so what we'll do is download and unzip the previously trained language model from the NLP Demystified GitHub repo. It's only a couple of megs. It's essentially a bunch of weights and a model specification. And we'll load it using Keras's load model call. Pretty easy. Alright, so here we have a function that'll use our model to generate text. It's not the most efficient function in the world, but it's good enough here. It takes the model and tokenizer. Keep in mind that in a proper production project, you'll want to save your tokenizer as well. It takes some starting or seed text and the number of characters we want to generate. And we'll get to temperature in a moment. Each subsequent character will be based on a moving window of the accumulating text. So here we're taking the last 100 characters of the text so far, if there is more than 100, and one-hot encoding them. We pass that to the model's predict method and get back a sequence. But we care only about the last character, so we'll pull the softmax output for that, which is a probability distribution, and from this probability distribution, the next character will be sampled like we covered in the slides. By dividing the log of this distribution by the temperature, we can control the shape of the distribution. When the temperature is below 1, the probability distribution sharpens, and the model will be more strict and aim to recreate the original text. When the temperature is greater than 1, the probability distribution flattens, and the model will offer more surprises and new spellings and phrases. And if the temperature is high enough, the output becomes nonsensical. What temperature works the best will depend on the nature of your corpus and your goal in using the language model, and there are a bunch of other sampling techniques in language generation that we'll cover when we talk about sequence-to-sequence models. Let's generate some text. For our first one, we'll seed the model with "bananas on the battlefield can," and set the temperature to 0.2, so fairly strict. Give that a try. It takes a while, so I'll fast forward to the output. Alright, so we have "banana peels on the battlefield can never come again into being," and from there it generates some pretty coherent text. I don't know for sure, but I wouldn't be surprised if this was just recreating the text word for word. What's amusing to me is that it's as if the model completes our seed text almost as a way to humor us, and then continues on its way to more serious business. Let's try generating more text, this time with a temperature of 0.5. Okay, we have "it's time to release the Kraken when the moon is in the constellations of the Sieves." You know, I think that is a good time to release the Kraken. From there, it's still fairly well structured. Alright, this time with a temperature of 1. So no influence from the temperature at all. Alright, so this time we have a few made up words, and the model's talking like it's had a few drinks. Alright, last one. With the temperature set to 2, we can see the randomness is getting closer to uniform, and the amount of nonsense has increased. Alright, so that is our language model trained on the art of war. A few cool things here is that it managed to sentence complete our seed text pretty seamlessly, and it, quote-unquote, learned things like spelling, grammar, punctuation, cadence, and even numbered bullet points, all from just trying to predict the next character. State-of-the-art language models operate on the same principles, but imagine this capability scaled up to hundreds of billions of parameters and terabytes of training data, along with more sophisticated engineering and sampling strategies. For further exploration, you can use the exact same flow to create a word-level language model. Perhaps you can download something from Gutenberg.org and try to use word embeddings for input rather than one-hot encodings. We didn't evaluate this language model, so another thing to explore is creating a separate test set, training your model, and researching how to calculate a Perplexity score using the test set. In this video, we moved from evaluating text as a bag of words to evaluating text as sequences. While using a bag of words approach can get you quite far and has the advantage of speed and simplicity, using a sequence processing approach such as RNNs can help capture the context found in the order of words. It also unlocks new abilities such as sequence labeling and language generation. There are a lot of ways to set up RNNs, and how we process inputs and generate outputs is dictated by what we want to do. An RNN that takes a single input and generates a single output is just a plain neural network. A many-to-one setup where an RNN takes in a sequence and generates a single output at the end is typically for classification. One setup we didn't look at is one-to-many, where an RNN takes a single input and outputs a sequence. We would encounter something like this in captioning, or as we'll see in the next module, decoders. By now, we're familiar with many-to-many setups where an RNN consumes a sequence and generates an output for each input as it would in sequence labeling or language models. But there's also a variant of the many-to-many setup where an RNN can take a sequence of one length and output a sequence of a different length. This setup is more commonly referred to as sequence-to-sequence or seek-to-seek. And there are so many important applications of seek-to-seek that in the next video, we'll focus on this setup and also learn about a powerful mechanism called attention.